Welcome everyone. Today we're going to talk about the final section of the course, which is on electricity and magnetism. And in order to do this, we're going to start with electrostatics, chapter 22. So you should begin reading this as soon as you get a chance. And of course you can work the problems on the Mastering Physics as you get time as well. So in this chapter we're going to talk about electrical forces and charges. Something of Coulomb's law of attraction between charges, and we'll talk about different types of electrical materials known as conductors, insulators, etc. We'll end up talking about electric field and what's called electric potential or electric potential energy. Then we'll move on to the next chapter. Electricity is a name given to a wide range of electrical phenomena. Most of you are already familiar with lightning or a spark created when we strike a match. It is also what holds atoms together, and within atoms it's what holds the negative charges of the electrons to the nucleus as well, and we'll talk about that as we go through. Electrostatic involves electric charges and the forces between them. The reason it's called electrostatics is because we are not talking so much about the movement or prediction of the movement, but rather how we create static charges. One of the simplest experiments ever done was with what's called pith balls. They're very small, lightweight, almost like styrofoam, but similar density, very, very low in weight. And the idea of them is that we found ways to separate charges into positive and negative. All atoms are electrically neutral, so we're going to talk about how we separate the positive charges within an atom from its negative charges. But this has been done in the past, and we'll discuss how in a minute. But the important feature here is that there are two kinds of charges. There's positive charge and negative charge. Just as you find a positive and negative terminal on a battery, it refers to the charges that accumulate on those batteries. We'll describe later, but suppose that we have been able to induce or create a positive charge on a set of balls, and we have on another set of balls, we have induced the opposite charge. And if we do this and we put these charges on very small balls hanging from the ceiling, what one finds is that if the two charges on the two different balls have the same sign, then they repel each other. So a positive and a positive will push away from each other. Normally, if there's no force at all, the balls will hang straight down under the force of gravity. But because of the fact that there's repulsion between them, they separate, and the distance between them increases until they reach an equilibrium where the gravitational force pulling them back in is balanced by the repulsion force. So whether there's two positives on two different balls or two negatives, they will both experience a repulsion between them. But on the other hand, if we bring a positively charged ball in contact with a negative charged ball, then they will be attracted to each other, and if they are attracted enough and they end up touching, they can neutralize each other, but as long as they're not touching, the charges will not cross over, and they experience an attractive force between them. Now, the origin of all charges has to do with how the atomic nucleus and atomic matter is made up of. It generally, for all the elements in nature, we can describe them in terms of atoms, which have a core center of particles called protons and neutrons, and this forms a very dense but very, very small core, and also a very heavy core of matter, which contains two types of particles. One is called protons, which have a positive charge on them, shown here with two of them, and the others, in this case the other two, have no charge, and those are the neutrons inside of the atom. Circulating around the atom, or the nucleus, are electrons, and they occur at various distances from the center, and they are oppositely charged, which are the electrons. So electrons are what we call the negative charged particles, and the protons are what we call the positives. And again, the electrons are held in their orbit about the nucleus because they are attracted to the core nucleus by means of the attractive force that occurs between them, and this holds them in their orbit much the same way as planets are held in the orbits going around the sun, which is a gravitational force that creates that phenomenon as well. Important facts about atoms: every atom is composed of a positively charged nucleus surrounded by this negative charge of electrons that's circulating, and each of the electrons in any atom has the same quantity of negative charge and the same mass. Generally speaking, every atom, as we end up in item number 1 again, we can think of every atom as being composed of a certain number of protons, neutrons, and electrons. In the lighter elements, they are all pretty much equal in quantity. So for example, if we have carbon, it will have 6 protons, 6 neutrons, and 6 electrons. Since the proton charge is positive and the electron is negative, but the magnitude of the charge is the same, that is to say the quantity of charge on them is the same, then atoms as a whole are neutral and they have 0 net charge. So if there are equal number of protons, and typically there are, in the case of carbon, for example, with 6 protons, there will be 6 electrons. And since protons have the opposite charge of electrons, the sum of all the charges adds up to 0, and that's what most of the matter looks like in the nature. We typically deal and work with uncharged objects like the chair or the table, or in most cases our bodies. So that's the general idea, and that is consistent with what we were just talking about. Some other facts are that not only compose the nucleus, but they are about 2,000, 1,800 times more massive than electrons. Each of the protons carries an amount of positive charge, which is equal to the magnitude of the charge of the electron. And neutrons have slightly more mass, but otherwise they don't really contribute to our study of electrostatics. That's the general scheme, and this explains why most of the matter that we deal with has no net charges on it. When in fact we are able to dislodge an electron from an atom, then the atom itself becomes positively charged. It has lost an electron. So for example, with 6 protons in carbon, then taking 1 electron off of the carbon atom, that would leave 5. So the net charge would be +1. 6 positive charges of the protons minus 5 charges of the 5 equal but opposite charges of the electron. And if, on the other hand, an atom is able to gain 1 more electron in its orbit around the nucleus, then it becomes a negative ion. And those are the 2 types that we have. So an atom which has lost an electron becomes a positive ion, and one that has gained an extra electron or more becomes a negative ion. Now, electrons in the atom they are structured so that if there are, say, 20 electrons in an atom, such as we find, for example, in calcium, then the inner electrons are tightly bound in inner orbit. Like, for example, Mercury is very close into the sun, but the orbit of Uranus and Neptune are quite far away, and they are not as tightly bound in their orbit as the inner planets like Mercury, Venus, and the Earth. And so similarly with electrons, the ones that are closest to the nucleus or the positive charge are more tightly bound, and those are called the innermost electrons. The outermost ones would be like the ones in the planetary system like Neptune and Uranus, which are farther out, and they're typically, those electrons that are further away are more loosely bound and can be easily dislodged or removed from their atoms. How do we create charges? Well, the simplest way to create charge is to rub 2 objects together. It works better if you choose your objects carefully to create the most charge that you can. A couple of common examples that one can do with ordinary materials is running your comb through your hair. And many of you have already experienced when you do that, you can create an electric shock or static, what we call static electricity, between the comb and your hair. So what's really happening here is that as you pull the comb through your hair, you are rubbing electrons from your hair to the comb. So your hair has lost some of its electrons, the atoms in your hair, and they become positively charged. And meanwhile, the electrons have been rubbed off onto the comb. the comb now has an excess of electrons and it has become negatively charged. So the easiest way to create this charge separation is by rubbing two objects together. Another example of that is rubbing a glass rod with silk. When you do this, electrons transfer from the rod onto the silk and the rod becomes positively charged, and therefore the silk accumulates the charges that the electrons that has been removed from the glass rod, and it becomes negatively charged, and the rod becomes, of course, positively charged. There's another important principle that's called the conservation of charge, and that is to say that when you do this rubbing process of rubbing either fur or silk against a glass rod, you have removed electrons from one object to another, but the total number of electrons has remained the same. So the total charge of the system is still going to add up to 0 in this case. Before we rub them together, the animal fur on the cloth is neutral, the rod is neutral, but when we rub them together, we separate the charges, and that means that some of the electrons, in this case from the fur, have been transferred to the rod, making this rod more negative. In any process, no electrons are created or destroyed. Electrons are simply transferred from one material to another. Now, an important relationship, getting back to that simple case we had with the two balls being attracted to each other, was an experiment first performed by Mr. Coulomb back in the 18th century. And basically what he found was that not only is there a force between these charges, but it depends on the separation distance between the two. So what he found was that if you doubled the distance between the charged objects, the force between them went down by a factor of 4. And if you triple the distance, let's say you just make the separation go from 5 centimeters to 15 centimeters, then the force between the charges would go down by a factor of 3 squared, which would be 9. So we call this an inverse square law. The distance between the force between them varies, depends, of course, on how much charge is on each object, but it varies inversely as the square of the separation distance, which is what I was just saying. We also, of course, what this is saying in the first part, is that the more charge I put on the rods or the balls, the stronger will be their attraction. So that is a fact that has been quantified by Mr. Coulomb in his famous equation that says that the force between static charges can be written as the charge on the first object times the charge on the second object divided by the distance between them squared times a constant k. And in this case, it turned out that k is a value that is given in these units, which is 9 billion Newton meters squared per Coulomb squared. So if we are able to, and we often do, measure the charge of an object in units of charge called coulombs, then we can correlate that with the force between two charges, knowing the charge on each one. And looks very similar to Newton's law of gravitation. This law also explains the bonding forces between atoms in a molecule, like, for example, sodium chloride, or often more commonly known as table salt. So it has a wide variety of application, but the basic definition is given in the famous force law that he derived. So according to Coulomb's law, a pair of particles that are placed twice as far apart, and by particles we mean charged particles, so we mean, for example, one of them has a charge Q1 and the other one has another charge, we'll call it Q2, that will be a certain number of coulombs, we'll experience a force between them. If we double the distance, if they are placed twice as far apart, then one of these four options will occur. The force between them will be half as strong, it'll be 1/4 as strong, it'll be twice as strong, or 4 times as strong. So based on what we said, which is called inverse square, if we double the distance, then the force between them is 1/2 squared, which becomes 1/4. So the inverse law says that the force between the two charged particles will be 1/4, and that's what we end up with. Now, there's one important difference between gravitational forces and electric forces. Electrical forces can be either positive or negative. The source of the force between them is what we call the charge, and electrical charges can be either positive or negative. And as a result, whether we're dealing with like charges, the forces will be repulsive. If we're dealing with opposite charges, then they'll be attractive. Whereas in gravitational forces, there is only one type of source, which is mass. Mass can only be positive, so there is only an attractive force. And it does not have a repulsive force, because we only have one type of mass, which is positive, whereas with charges, we have two kinds of charges, positive and negative. So another way of creating static forces or electrical forces, suppose that we rub an inflated balloon on your hair, which you may have done in the past. You could place this balloon on a wall and notice that you can make the balloon stick to the wall. The balloon sticks to the wall because the charges, the excess electrons on the balloon, will migrate towards a wall which has positive and negative charges built into it from its atomic structure. And the positive ions, or I should say the electrons, are repulsed away from the electrons on the balloon, leaving behind the positively charged ions on the wall, and that attraction holds the balloon to the wall because they are attracted. And again, we do this simply by rubbing two objects together. In this case, the balloon against your hair. That's the one scenario in which we actually are able to create what we call charge polarization. The charges in the wall have been polarized. Also, the charges in the balloon, the negative charges are attracted to the wall, and the positive ions that are left because of the repulsion of the blue electrons leads to that static attraction. So among the different materials that can accumulate charge, we distinguish them into two different classes or categories. One which is called conductors and the other which is called insulators. So a conductor is a material in which one or more of the electrons in the outer shell are not well anchored to the nuclei, and they are basically free to wander in the material. This is typically true of materials of common conductors such as copper, as used in copper wire, aluminum, gold, silver, iron, all have loose outer electrons which are able to migrate through the material fairly freely, and therefore these are called conductors. On the other hand, we have materials in which the electrons are bound tightly to their nuclei. They are not free to move. They are not free to be dislocated from the central nucleus of the positive charge. And because of the fact that they are strongly bound onto their atoms, they are not able to move, and therefore they do not conduct electricity. And so conducting electricity basically means that if we connect the battery to two ends of a rod, the positive terminal of one battery to one end and the negative terminal to the other, with a conductor we would get a flow of current of electrons going through that material, whereas with insulators we would not be able to get that flow, and therefore they do not conduct electricity, and we call them, or by electricity we mean a flow of electrons, and they would be called insulators. And there's another class of materials called semiconductors. It's a material that can be made to behave either as an insulator, or sometimes it can be slightly conductive. It's never as conductive as a copper or aluminum bar, but it can have some conductivity, and it falls in the middle range of electrical conductivity or resistance. If you want to look at the opposite of conduction, we call that resistance. It's in the middle range between a true insulator and a true conductor. The semiconductors are used quite frequently in electronics. We use semiconductors are fabricated. Well, they also exist in nature by themselves, such as silicon and germanium, but they're more useful when we modify them by putting additives in and make devices called transistors, which are used in radios and in amplifiers. So the semiconductor industry is huge. It accounts for a very large fraction of the gross national product in our country, and they play a dominant role in commercial enterprises. All of our electronics equipment, including the camera that's being used to film this lecture, have enormous numbers of semiconductor materials in them in order to function. Then there's another class which we call superconductors. These are materials that can acquire zero resistance when we lower their temperature to a very, very cold environment. And by cold, we mean temperatures very close to absolute zero, or of the order of minus 460 degrees Fahrenheit, something that we can only do and create in the lab. They are used in cases where we need to have extremely high current flow, but we don't want to heat up the wires that carry the current, because that would cause them to melt and get destroyed. So the superconductors can handle, because they have zero resistance, they do not heat up, and they have enormous current capabilities. And the most common example of this superconductor is in the use of MRI magnets. So if you ever go to the clinic and have to get an MRI scan, chances are that for sure they will have a magnet that is made up of superconducting wires to create a very, very strong magnetic field. And there is no heat loss, so they don't heat up, and they don't require any significant amount of electrical power in order for them to operate. So these are useful devices as well, and they're materials that are used when you need very high current and zero resistance. So the couple ways in which we can charge an object, which we've already discussed, we can rub two objects together like silk cloth on a glass rod. We can also take animal fur, hair, and rub it on against a rubber rod, and that would also create charges, separation of charges, and we could charge up one object to the other. Of course, the other thing you may be familiar with on very dry days in the wintertime is when you rub your feet on the carpet at home, you can build charges up from the carpet onto your body, and you go over and touch a metal object and you get a spark. And that is the case of electrons leaving your body and going to a metal surface. So that gives what we call discharge. The other way in which we can do this is electrons can be transferred from one material to another simply by touching. So if I have, for example, a negative charged rod and place it in contact with a neutral rod, then some of the electrons will move to the neutral object and therefore become charged. The original object will become less charged. The uncharged object, the neutral, will acquire some of those electrons. So each rod might get half amount of the charge that the other one started with, but the contact will allow the electrons to move from one to the other. The other way in which we can create charges is what's known as induction, charge induction. And in this case, we consider two insulated metal spheres. Insulated metal spheres. So that means that the bases are made up of insulators, so no electrons can move into or leave the spheres that you see in the pictures here. They can, when they touch they can touch each other, so in effect they form a single uncharged conductor. So we start off in case A, lower left. The two uncharged spheres are in contact with each other. They have no electrical charge on them at all. They were neutral to start with. They're neutral when they're touching. But now what happens is we bring one of our rods over with negative charges on it that we have either gotten from rubbing one of our rods to acquire that charge. And when it's brought near the sphere on the left in figure B here below, that was sphere called A, then what happens is that the electrons from both spheres are repelled from the electrons on the rod, and they move to the furthest distance they can away from the rod and move completely over to the right of object B. That leaves object A with a deficiency of electrons, and object B has a net positive charge on it. At that point, we separate the two. They're no longer in contact with each other. The negative charges on B stay on object B. The lack of electrons, or therefore the positive charge resulting in object A, the sphere A, is positively charged. And now I just remove the object that created the induced charge altogether, and I have two separate spheres, one which is positively charged and the other is negative charged. So this is another way in which we can create charge separation, and it works very effectively.